Okay, so I recommended on this example that you literally make a code comment on every single line so that you could understand what was going on. So here's my quick walkthrough of my comments I made to myself. So the add-I SP-16, that's just allocation of stack space as usual. These three instructions, the WPC add-I and LD, that is just loading up some value from a hard-coded constant location somewhere after our code. And if you looked in the debugger, you would see that this read from offset 0 from that, or the load from offset 0 from that, is basically our A-low. It is our dissected. So it pulls dissected into A2. It immediately stores it back out at SP plus 0. I'm going to interpret this as essentially this is the local variable A for its initialization. And then it also reads from A3 plus 8, and it loads that in to A3. And so that is the A high. That is, if you looked in the debugger, that is going to be a 0. And so this is going along with the notion of, well, we just wrote dissected in our C source code, but it's being stored into a 128-bit variable. So it's going to be upcast into a 128-bit value, and the upper 128 bits are 0. So that A high was 0, pulls it into the A3, and then immediately stores it back out to stack pointer plus 8. And I'm going to treat that as the upper 64 bits of A high. And then because this is unoptimized assembly, it immediately loads that value back in from SP plus 8 into the A2 register. Then it's going to do another WPC add-I and load to pull from a different location. So that's not that location, that's a different location. And that is just the delectable. That is the hard-coded constant delectable, which we're going to call B-low. And it pulls that into A3. And then here is our first multiplication. We have A2, which is the A high at this point. A2, A high, times A3, B low. And so this is going to give us the lower, because it's a normal multiplication, the lower 64 bits of A high, which was really just 0, times B low. So the net result is really just going to be 0. But in the context of that overall diagram we saw, we knew that there were going to be 64-bit multiplications that would yield a 0, but we wanted to keep the lower, just kind of visualizing, there was the lower 64 bits of the one, there's the lower 64 bits in the one, and then there's the upper 64 bits of the other, if you can picture back to where that diagram would have been. But anyways, the net result of this is you can either think of it as the math of A high times B low and keeping the low 64 bits, or you can say it's the literal 0 at this point. So A2 stores that result. Now it is loading up into A3 from stack pointer plus 0. We have to walk backwards and see where do we store to stack pointer plus 0 right here. So it is loading up A low into A3. And then it is loading an immediate to A1. And I think this is kind of the compiler just recognizing like, hey, I don't need to grab the A high from this delectable. I know it's just going to be 0. And so it just, instead of doing an extra, like this is again, they could have done the same thing up here. I don't know why they did it down here, but they just loaded an immediate because they recognize that the upper 64 bits are just going to be 0. And here it seems like, well, that's a little more efficient. And so again, it's just unoptimized code. This was a little less efficient. This is a little more efficient. Why they chose it to do one way, one place and not the other, I don't know. But I believe that this is basically in the same way this is setting A low, this is setting A high, which it understood to be hard-coded to 0. And so then it is doing A low, so A3 is A low, A1 is B high, A low times B high, which is a hard-coded to 0, and that gives you then the lower 64 bits of that going into A3. Then it is going to add A3, which is this thing we just did right here, so lower A low times B high, lower A low times B high. So A2, which is from earlier, the A high times B low, the A high times B low, and so it's basically all of this math done together, but really the net result is 0 because both of those things led to zeros. But you can see how it's doing the multiply, and then adding. And these were sort of the first addition of those two adds that are necessary to get the upper 64 bits. Okay, so now it has got A1 holding this math right there, and really just a literal 0. Now it's going to load back the A low from the stack pointer plus 0, put it into A2, another WPC, and it's going to get the B low out of the area beyond here because it didn't save a copy in a register anyway, which it could have totally done because it has so many registers, it could have, but again, this is unoptimized code. So it pulled in A low, it pulled in B low, and we know that the last sort of multiplication that's necessary to do the additions that we saw in our diagram is you're going to have multiply to get the lower bits, so the lower bits of A low times B low, and multiply to get the higher bits of A low times B low. So A2, A3 are just A low, B low, and so this one is going to store the high bits into A3. So at that point, you now have like all the bits that you need to add to this other thing and get the net result. So there's a little bit of moving around that's going on. So then it's going A0 into A4. Well, what does A0 go up here? Okay, that's the result of this lower 64 bits. So that goes into A4. Result of this higher 64 bits goes into A5. Then it's adding A5 to A1. So A5 is the high bits. A1, if we backtrack back to here, we see that it is these. It is the lower 64 bits from two multiplications, but essentially it is that diagram that we have. I guess I will go backwards and show it to you. Right, we're doing this calculation plus this calculation. We're keeping only the lower 64 bits. We don't need these upper 64 bits. So do this multiplication, keep the lower 64. Do this multiplication, keep the lower 64, add them together. And now it did this multiplication, and it's adding the upper 64 to the sum of those two things, and that'll give it the upper 64, and then it's just going to have the lower 64 there. So continuing on. We are right here, and we are doing the addition of all of that stuff together, and that A3 is going to be our ultimate upper 64 bits of the 128-bit result. Then just some moving around, A3 into A5, store the A4 value, which was back from here. It was this low times low. So store the low times low back to the stack, store the A5, pull them back in. So this is just unoptimized moving around. We wrote it out, we read it back in. We moved it between registers, A4 to A2, A2 to A0, and that means ultimately that is going to be our lower 64 bits of the return value. And same thing, A5 to A3, A3 to A1. A1 is ultimately our upper 64 bits. So that's why I went to the trouble of showing you that indication of, here's our visualization of what kind of multiplication could happen for a 128 times 128 where you only stored the lower 128. This is what led to our 3 multiplies and really 4 multiplies because we have to do separate ones for lower bits and upper bits. So hopefully if you wrote a comment on every single line and you recognize that there was this kind of thing going to be going on, then you saw that exactly this is what was going on in the assembly.